So yesterday we saw that when we have some real world data, so then we have to decide how we want to represent that data so that a computer can work with it, right? And we saw that many of these representations, they naturally give us vectors, matrices, tensors, and so on. Right? But even then, there are some choices to be made about how you want to represent that data. Like, for example, for text, whether you want to represent it as a sequence of alphabets or a sequence of words, right? And if you choose it as a sequence of words, then how do you represent each word? All those factors sort of become important, right? So today we are going to see that, we are going to consider the situation where we have, let's say already we have taken some data, we have represented it as a bunch of vectors, let's just say. So before I go there, maybe I should say something. So yesterday we saw that we can take the data and we can represent it as various objects, like linear algebraic objects, like, so vectors or, matrices, or like some 3D tensors, 4D tensors, something like that, right? So one of the first things we are going to do today is, first we are going to assume that all data is being represented by vectors. So everything will be interpreted as vectors. So what would be the easiest way to interpret a matrix as a vector? So there are two ways. So one way is that you take each column, right? And then basically you just write down the first column, then the second column, and so on. Well, so this becomes a long column vector. When I wrote it as a row vector here, but so if you take the columns and stack them on top of each other, right? So this is the first column, second, and then this whole thing becomes one long vector, right? And what is the dimension of this vector? If this was some n cross m matrix, so it's a vector of length nm essentially. So same can be done for this 3D tensor and other things. So 3D tensor, for example, shows up when you're dealing with, say, images, right? In which case, you have the length of the image, the breadth of the image, that's the matrix form. And then you have these red, green, and blue. So these are called channels. Right? This is just a word. So you have 3 channels, and then you have these one matrix per channel. Right? So then first you basically take those 3 matrices and maybe stack them on top of each other or something. Or maybe you first make a long vector out of the red, then a long vector out of blue, then a long vector out of green, then stack those things one after another. So you get a much longer vector. So there are many ways of doing this, right? Depending on the number of dimensions of the object you're working with, you can choose which dimension to stack and how. But at the end of the day, you have to choose one method, and any of these methods are fine, right? But you just have to be consistent throughout your whatever. If you're writing a software or something, so naturally you have to choose one convention and stick to it. So this is what I mean when I say that whatever data I'm dealing with, first I'm going to assume that I have figured out some way of representing the data using these objects. Second, I'm going to assume that that representation can be converted into a vector in one of these manners. So at this point, all data that we are dealing with can be thought of as vectors. So once you have these vectors, you can sort of think of these vectors in some vector space, like, it's something geometric, right? So these are like some points in some space. So here in this, in the figure that you see in the slide, so we have some points. In fact, we have a lot of points. So each of these things represent some data point, right? So, for example, if you're, let's say, classifying, sentences like some tweets, you have a database of tweets, then you can convert each tweet into a vector, right? And then you can plot that vector in the vector space. So here, all the points are represented in 2D space. That's not going to happen for your tweet, but this is just a figure just to help you understand. Okay? So you can think all of these as tweets, and maybe you want to classify them as positive or negative, right? So then these are like negative tweets, these are like positive tweets. And because of the way, whatever way you chose to represent your data eventually led you to, these tweets being distributed in the space in this way. So in this way, so this is like anything can be sort of represented in this way. And we are basically focusing on a very simple task, which is just classifying things. And even then classifying it into just two classes. Right? This is in some sense the simplest possible thing that you can do in machine learning. Right? Okay. So just to quickly recap, we think of our data as points in some vector space. And since we are just classifying these points into two classes, we just need to, the points are maybe, so they either fall in the positive class or negative class or something like that. And your task would be that you'll be given something and then you have to figure out whether it's positive or negative. So in this figure that you see, these positive and negative things are sort of separated by some complicated curve. So in this case, at least there is one curve which is sort of saying, things on this side are negative, that side are positive. This is a more complex example where this side is positive, that side is negative, but then there are some negative things on the positive side here and over there. So this is also possible. So your data, this is a function in some sense of the representation that you have chosen for the data. Right? So if you choose a good representation, hopefully things will become simpler and simpler for you. If you choose a bad representation, then things will start looking more and more like this. Okay? But in any case, once you have made a choice based on whatever you have thought, you will get some representation of the data. Right? And now you have to process that data and do something with it. So in machine learning, the way it works is that, well, a priori your algorithm does not know anything. So the algorithm has to be shown a bunch of examples of what are positive things and what are negative things. And from those examples, it learns, how to classify unknown things, unseen things as positive or negative. So to be more, to go back to our example, so if these were some tweets, right? So maybe you can think of these as tweets from last 1 year, right? So up to December 2023 or something, which have been manually or somehow classified as positive or negative. So you will take these tweets and you'll give it to your machine learning algorithm, the classifier algorithm. The classifier algorithm will process these tweets and figure out some things. It will figure out some numerical parameters essentially. And then when you give it a tweet from 2024, which it has not seen before, it will apply those parameters or whatever the algorithm is going to do to classify that as positive or negative. So the data that it is given to learn from, that is called naturally the training data set. And everything else is called the test data set or whatever you want to call it. So we don't want to go into the details of those things, but at least training data set and the non-training part is clear to you. Yeah. So in the real world, whatever data you are working with, when you try to even break them into two classes, you are much more likely to see this or that rather than, something much simpler. But we sort of have to begin with the simplest possible scenario. So we want to start with a scenario where there is some classifier which separates positive from negative and it is linear. So this is a non-linear classifier. Even if you don't know what is linear or non-linear, intuitively, this is a line and this is not a line, this is a curve. So this is what I mean. So in 2D, a linear classifier literally will be a line. And this line is going to separate the positive points from the negative points. In higher dimension, it will not be a line, but it will be a hyperplane. Right? So if the data were in some 3D situation, then it will be some 2D plane in the 3D space separating positive from negative. If it is 4-dimensional, then it will be a 3-dimensional hyperplane and so on. So it's not easy to visualize higher dimensions, but we can see in 2 dimensions and this is what it's going to look like. So right now we are not in a position to learn or figure out, these sort of classifiers, but we are in a position today we will see how we can learn this sort of classifiers. Right? And then we'll try to sort of approach how this can be done. So we are starting with the simplest possible case of classification algorithms, where the data is geometric in nature, as in I have represented it as a geometric data. So essentially there are some points in some space. And our goal, so we'll be given some training data set where the points are labeled as positive and negative. And we are sort of also assured that there is some linear classifier separating the positive from negative. And we are supposed to find one such classifier. Right? So given a set of data points, actually there are multiple possible linear classifiers. Right? Our goal is to just find one of them for today. So any questions about anything here? Everything, like everyone is okay with the setup here. So, I mean, this was just the recap of, whatever we discussed yesterday in some sense, but let's just do it. So as I said, each input is just a vector of some length n, right? So here in the figure, it is 2-dimensional. So there will be just x1 and x2, like two coordinates. And we want to find a linear separator. So linear separator in 2D will be defined by a line. In higher dimensions, it will be a hyperplane. And hyperplanes are always written, it's easiest to think of them as this equation, right? So w dot x plus b equals 0. So b is a number. W would be essentially, like you think of a line, right? So what is the equation for a line? Y equals mx plus c, right? So c is some constant, m is also some constant, and it's just multiplication with x. So this is basically the higher dimensional form of this. So here instead of mx plus c, you have w dot x plus b, right? So x would be, the coordinates of a vector, right? And so this will define a hyperplane. So, right? So our goal is to essentially figure out the values for w and b given the training data set, so that hyperplane that we figure out separates, the positive and the negative sample, the data points. So everyone is okay with the definition of hyperplanes? Like anything that I've said so far that is unclear?
So it's the separation based on the value of w.
Correct. So before I go to the separation of these points, I just wanted to make sure you are clear with the definition of hyperplanes. Yeah, and then the separation part comes here. So if a point is positive, then what will happen is that when you substitute the coordinate of those points for x here, right? So the value that will come out of this equation, that will be a positive number. Right? If that point was a negative data point, then the values that will come out will be some negative number. So our classifier uses a linear separator in this form, right? So the hyperplane itself is defined when this equation is equal to 0. It's for those values of x where this equation is equal to 0. And for other points, if the value of the equation comes out to be positive, then they're classified as positive points. Otherwise, they're classified as negative points. Right? So this is how this hyperplane is classifying the set of points in this vector space. So, is this clear? Right, so you already know dot product, so no need to go into this. And then dot, instead of writing it down explicitly, you just write it like this. So here is an equation so you are given a set of, data points with their labels, which is either +1 or -1, let's say. That is your training data set. And from this training data set, you want to figure out a linear separator, a hyperplane, for which the equation for that hyperplane will evaluate to positive for the positive points and negative for the negative points. This is what you want to do. And here is an algorithm for doing this. So start off with the value of w being equal to 0 and including setting b also equal to 0. Right? So initially it's just some default hyperplane. Now, while there is, now take one training data point, right? If this training data point is being misclassified, right? So suppose it's a positive data point, but w dot x is strictly less than 0. Right? Or it's a negative data point and then w dot x is strictly more than 0. Then what you do is that you update w, right? You add xi, yi to w. Right? So yi is a number. This number is being multiplied with the coordinates of this vector xi, and that is being added to w.
If y is equal to +1, then what is the product of next and nego?
No. So the point is that the classifier is right now misclassifying this point. So only when it is misclassifying the point do you do this. Otherwise you don't do anything. If it is correctly classifying the point, you move on to the next point essentially. Yeah. Right. So sorry. So I was going to come to this point. So here it is here that things become a bit more complex. So let's just go back here, right? So in 2 dimensions, when you have these points, and I have drawn this hyperplane, right? You can see that, well, this is not actually an hyperplane. It's like a shifted hyperplane. It's not passing through the origin. As in, this is not a subspace of the 2D space. So if I have this extra b, it sort of becomes more inconvenient. So what we do is that we sort of bring this b inside, right? So what I do is that I take each x and add an extra coordinate. Do I want to do that? So that I can simply write down the equation as wx. So see, look at this equation, right? So you have this equation for line w dot x plus b equals 0, right? So I can simply think of this as w dot x plus b times 1 is equal to 0, right? So then I can think of a new vector. So let me write this down. So I'm saying w dot x plus b equals 0, which is to say w1 x1 plus w2 x2 plus wn xn plus b dot 1 is equal to 0, right? Which is the same as saying take the dot product of these two vectors, w1, w2. So this is the first vector, right? The second vector is x1 . Sorry, this should be a. Sorry, this should be a. Okay. This should be LD. Right? So I have written it like this. So I can think of this as some w prime dot x prime is equal to 0. Right? So I'm just interpreting this whole thing in a higher dimension. Right? So now if I do that, then my life becomes much simpler. So in this way, my data was in 2 dimensions in this example here, but I sort of look at it as a 3-dimensional object where at the last coordinate, I just put an extra 1. And then I can think of the linear separator as like a true 2-dimensional subspace of a 3D space. So life becomes much simpler for me. Otherwise, I have to play with that. So this algorithm becomes more complicated to write. Okay. So when we are saying w is equal to this, so think of this as the length of w, the dimension of w is 1 plus the dimension that we are seeing here. And this 1 is for that extra b. Same with the data points, where xi has an extra 1 sitting at the end. So once you do this, then this b in this thing, it goes away. So there is no more. Oh, it doesn't work here. So there's no more b here. So I just have this simple equation. And once I have this simple equation form of what I want to achieve, I want to find a w so that for all positive points, w dot x for that positive point is a positive number. And if that point is negative, then w dot x of that negative point is a negative number. Right? This dot product is a negative number. This is all that I want. I want to find such a w. Then here is my algorithm to do that. Take one of these points in my training data set. Now it could be, the label could be +1 or -1. If the label is +1, then I would like w dot x to have a positive label. So what will happen is that it will have a, like this would be less equals 0 here. Then what I do is that I just add xi to w. Right? I mean, I multiply xi by yi. Y is just 1 because it's a positive sample. So xi is being added to w. Now, if it were a negative sample and this happened, it was again misclassified, then I'll have w plus xi yi, right? Here yi is -1, so actually I'm subtracting xi from w. So that's what, yeah.
First is, because in Europe, this is 0 only will come. The first things, installation W will be taken that because W is taken to xi.
I mean, we have to start from somewhere, right? And 0 is just a... Which xi related?
You are taking it our first data set.
Yeah, okay, sure, I can take that. But I'm just saying that happens naturally in the very first. Right, so whether I do it explicitly or I start like this, immediately it will happen. That's why, I mean, just for the sake of keeping this as short as possible, I didn't write that. Yes. What you are saying will immediately happen. Right?
Yes.
Yes. So you're saying you have one iteration, but I mean, I will have thousands of data points. So doesn't, I mean, you're correct, but it doesn't really make much difference. So this is my algorithm. And it's a very simple, as you can see, it's just adding some vectors to some other vectors. And that is all it is doing. And the claim is that it will eventually find a linear separator for the given training data set if there is a linear separator. So everyone is okay with the algorithm. You understand the whole setup, like why B has disappeared, why blah 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 the way. So shall I go to the next step? So by the way, this algorithm, as you can see, this keeps running until every point in your dataset is being correctly classified with the current W. At that point, you stop. As long as there is a point which is misclassified, you update W. When no point is misclassified, you stop. Right? So this is the algorithm. Now, if I don't show you anything, so it is not clear why the algorithm should even stop running, right? So I have maybe 10 data points. So I update W to fix it for the first data point. That might break W for the second data point. So update W to fix the second data point. It breaks it for the first data point, right? This can keep happening in a loop. And I mean, it could happen, right? So because there is no other termination condition. But we have this theorem which says that if the data points that are given, they admit a linear separator, then this algorithm will definitely terminate. Right? And we can actually quantify how much time it will take you to terminate. That time will depend on a bunch of factors. One factor would be how much is the gap between the positive and the negative points. If they're very, very close, which means that the task of separating these 2-point data sets are, it's more challenging because they're very close. So then the algorithm is going to take longer. Another factor would be how far, like how large these, the length of these data point vectors are. Right? If they're very, very large, that is also going to impact the running time of this algorithm. Because if the data points are not linearly separable, then we cannot do anything. Right? We are working in the setting where we can linearly separate the data. We don't know, but we assume it is linearly separable.
Suppose my algorithm is not converged, we can ask that in special case.
No, maybe you have some good reason to believe that the data is linearly separable. Right? Whatever data you are working with, you know something about the data, right? So maybe there's some good reason to consider that it will be linearly separable. That is all essentially. So there are also more complex algorithms which can handle, some amount of noise, some positive point, a few positive points here, a few negative points there. But we'll not go into those complicated algorithms in this in this workshop. So we are simply going to assume that the data is linearly separable, and then we are going to try to find a separator for that linearly separable data. Okay. So I told you the algorithm, which is just adding like vectors essentially. So let's now see the formal statement for why, like this theorem formally will prove that this algorithm terminates, and it will actually quantify how long it takes for it to terminate. Right? How many steps does it take? So let's say there is some special W star such that, okay, so let's say there is some special W star, like we wanted to find a W such that for each data point W dot X, each data point Xi, W dot Xi is positive if the corresponding label Yi is positive, and W dot Xi is negative if the corresponding label Yi is negative. So then I can also state this as saying W dot Xi times Yi is always, positive. Right? That is the kind of W you want to find. Now I'm saying suppose there is some special W star which additionally has the property that W star dot X times Yi is at least 1. So whatever solution you find, which could be some W, this could be some number which could be say 0.05 or minus 0.05, right? So that is not suitable for this W star. So W star has to have this property that it is at least 1, right? Which is to say W star dot Xi is at least plus 1 for the positive samples, and it is at most minus 1 for the negative samples. So can you tell me, if I give you some W, how could you compute a W star out of it? Suppose I give you one W which satisfies this thing. The W dot Xi is positive for all positive samples and W dot Xi is negative for all negative samples. Then how do you get a W star from this W?
There are a number of data points with you.
So why will that ensure this property?
This actually gives us a mean type of thing actually. I think we error not minimum actually, but somehow
No, what's can you maybe give an argument for why this?
this time till I don't know actually.
No, that's okay. So I mean, whatever argument you're thinking.
There are different W possible perfect choice actually.
Okay.
I'm taking for each of the data point that is training data point. I'm given W1, W2, and W100.
No, you only want W. W is a vector. So you're not given some 100 W's. You're only given one W.
Only. Suppose it's n by n, that means we keep the 1.
Oh,
So 1 times by n.
you want to add 1. See, okay. So for the positive samples,
W is in vector length sensor.
here
I take the W star is n plus 1 finals.
final is 1. Okay. So then what impact does it have on this equation for W star? So if Xi Y is a positive sample, so then what will happen to W, this W star that you gave me at Xi? That will be more, if we keep growing. It will keep growing, is it? Like the value of W star Xi Y will be more than 1. Okay. Because you have added extra 1. Okay. Now what if, this Xi is a negative sample, then what will we do with the structure? So if the value was minus 0.5, what will you get now?
It will be the negatives.
Why?
W star positive is
Is on negative now, minus 1.
Right.
Sin.
But you're not multiplying Xi in Y, multiplying per saying the dot product, that is the number. You multiply that and what? Another way of saying this is that w dot xi is a negative number.
Is
No. Oh, sorry. Okay. I is, okay. So just say x, y is some data point. Forget that. X is a data point. Xi was some like you have like one of the data points. Yeah, it's not the row. It's just one of the vectors in your data. Oh. Okay, so let me tell you what we should do. You have some w such that w dot x times y is greater than 0. So this takes care of both positive and negative samples. So, I mean, you're given such a w. Why does it take care of positive and negative samples? Well, for positive samples, y is +1. So, w dot x is also a positive number. So, positive times positive is positive. And if xy is a negative pair, then y is -1. Right? And w dot x is a negative number. So, negative times positive, negative times negative is a positive number. So, in both cases, w satisfies this equation. And this w is given to you. From this w, you want to get another w star, which will satisfy this, right? So you are given a w that satisfies the thing on the left. You want to get a w star that satisfies the thing on the right. So the way to do it is, you go over each choice of this xy, all the training data points you have. For each data point, you see what is the value that you get, right? And take the minimum. Take the minimum value that you get out of, this expression. Like this expression. Say that minimum is some lambda. So if I take this equation and divide, if I write, then what value should I expect for any xy? I should expect at least 1. Right? So this is something you can easily prove. Right? If you are not convinced, you can go and try to prove it and you will be able to prove it. Yes, so the theorem starts by assuming, suppose there is a w star which satisfies that thing we want. Right? So I'm saying, how do you get this w star? To get this w star, you can start with a w. I assume that the data set was linearly separable. So there was some w which satisfies this equation for every data point. From that w, I will find out the minimum value of this expression and divide by this expression. So w star is simply w divided by lambda. Yeah. So that would be the w star. And this w star will satisfy this requirement as we want. So therefore, the assumption of this theorem is it's simply assuming that my data is linearly separable. That's all. Okay. And in particular, we would like to choose some w star which has small values in it. But I mean, okay, that will come out later. Right? So, but the thing is that we can start with some w star. And this existence of w star always comes out of the assumption that our data set was linearly separable. So, suppose we have this, then the claim is that perceptron algorithm, so let me just go and remind you once, which was simply this, that whatever w you have, you run through the data set. If any particular data point, here xi is a vector and yi is also a vector. Okay, so it's written like this here. If any particular data point is misclassified, then just add xi times yi or xy to w. Right? So for positive samples which are misclassified, w will become w plus x. For negative misclassified sample, it will become becomes w minus x. Right? This is how you change w for a misclassified sample. And you keep doing this over and over again until everything is correctly classified. Right? So this keeps running in a loop. So this theorem is saying that that algorithm which keeps running in a loop will run at most these many times before it stops. Where this many times is the first is the length of this W star vector that we just derived. Second, this R square is the length. R is basically the length of the largest vector in your data set, the largest x in your data set. Right? So the running time or the number of while loops that will happen in this algorithm, that will be at most this much. The square of the product of R and W star, like length of W star. Okay? So let's try to, so R is defined here. So let's try to prove this, right? So the proof essentially works by keeping track of two quantities. The first is that, okay, so here W star is the thing that we have from here. So, and while we are running the algorithm, we have this vector W, which is always being updated. So what we do is that we keep track of these two numbers. First is just the length of W that we have in the algorithm. Second is the dot product of W and W star. So let's look at these two quantities as the algorithm keeps running. So the first claim is that every time we update W, this quantity W dot W star, which is the same as writing W transpose dot W star multiplied with W star, that increases by at least 1. Okay, each time I update my vector W, this quantity, this W dot W star will increase by at least 1. Okay, so what is the reason for this? So because I have updated W, so W has now become W plus XY, or I here is basically, so XY, right? So if I expand this out, what do I get? I get this term, the dot product with the previous W, and then this, right? And what do we know? We know that this is at least 1, right, by this, right? So this value has gone up by at least 1. So this is a very straightforward consequence of, what we had in the theorem, like our assumptions in the theorem. Okay, so the second quantity that we keep track of is just the length of W. So the claim is that the length of W increases by at most R square, where R was the length of the largest X vector. So how do you measure the length? So how do you write down R square, or how do you write down W square? So that is simply W times W, right? So when I update W, then it's W plus XIYI times like dot W plus XIYI. If I expand this out, I get the length of W square, I get this quantity, and then I get XIYI square. Now, if you look at this quantity here, I claim that this is a negative quantity. Why? I mean, this is at most 0. Why? Because I updated W, which means that this point was misclassified, right? So if you look at this, so this is yi is just a number. I will just pull it out here. So 2yi times x dot W, right? So if this was, if x, or you can look at it here, right? Because the point was misclassified, this quantity is less than 0. It's negative, right? Here we were assuming that everything is being correctly classified. That's why it was positive. Because it's not being correctly classified, it's negative, right? So this is a negative quantity. So if I just drop this negative quantity, then I just have W square and this square, right? Here yi is just plus 1 or minus 1, so it has nothing to do with length. And this is just the length of xi square, whose maximum value is R square, right? So whenever I do an update, this quantity W square increases by at most R square. Okay? So everyone is fine with this and this point? Yes.
keeps increasing. Do you mean that the vector gets more and more weights added into it?
I mean, it does get added or subtracted, right?
I'm not saying the value changes, but what do you mean by increase in the length of the vector?
So W is a vector, right? Which I changed by adding XL. So then I get a new vector.
Yeah, but why is the length changing? I'm not understanding.
What do you mean? If I take a vector and add something to that vector, won't the length of that vector change? The new vector is same. Is the length of some A plus B the same as the length of A? Therefore, that is bounding the length of A plus B. Right? This is the increase in the value of this vector when I make an update to it. And by making an update to it, it means that I'm adding something to the vector. Like adding this vector to that. That's all. And I'm not saying it is increasing by at least this, but rather by at most. So it might use, in fact, does not decrease at all. Or decrease or whatever. But it does not increase any more than that. That's all. So let's see how we can leverage, these two things to get what we want. So let's say this perceptron algorithm makes some M updates. Right? So then the first fact, which was saying that in each update, the W that you have times dot W star would increase by 1. Right? So if you make M updates, then the current W dot W star would be at least M. On the other hand, the length of the W, like the length square of W, that would be at most M times R square. So what I can do is that I can basically try to substitute for M. I want to substitute one of these things into this other equation and get some relation on M. Right? So I can write down, so this is the equation that is being written like this. Right? So why can I write this? Because M is upper bounded by the value of the dot product of two vectors. Dot product of two vectors is length of those two vectors times some cos theta, the angle between them, which varies between 0 and 1. Right? So therefore, this is definitely true. This is a consequence of the dot product. Right? And then I move this length of W star over here. Right? And I replace the value of W from this equation. Right? So I get this. So therefore, when I, so what do I get? I get a square root M here. So I can divide by square root M, and then I get this root M is at most R times W star, like the length of that vector W star. So if I just take the square, then I get M is at most R square times the length of that W star square. Right? So the number of updates that can happen in the perceptron algorithm is upper bounded by this. After at most these many updates, it has to terminate and find some linear separator.
Then also the update is also able to help the user.
Yes, the number of updates required to reach a solution depends on W star. So as I said, W star essentially is a function of how close the positive and negative points were. Right? Which came about because how did I write W star, right? If you give me a W, I will divide W by some lambda, which was the minimum distance between the separator and some other point. So if the points are very, very close, then that minimum distance is also smaller and smaller, which means 1 by lambda is larger and larger. So the length of W star would be larger and larger. So this is the algorithm itself is very simple, just add some vector or subtract some vector or something. But it is just very interesting that it terminates, and in fact you can prove some explicit bounds on it being terminating a solution. Right, so I think I will stop here. So essentially there are more things to say about, because there are multiple linear separators between two set of points, we take any line slightly twisted in this angle or that angle, shifted a little, right? you'll get another separator most likely. So which one does the algorithm find? So the algorithm finds one of these things arbitrarily. We don't know. So if you'd like to find a line maybe which is sort of equidistant from positive and negative samples or some other criteria like that, then you have to come up with a more complicated algorithm. So we will not go into that. We will stop here. But this is an example of how, using very simple linear algebra, you can come up with a classifier. And you can even prove that this classifier finds a solution like essentially, fairly fast. So one of the things you may notice is that the time required for it to converge to a solution is not dependent on, for example, the dimension of the data. You will pay for the dimension in doing all these dot products and other things, but it does not figure in the number of updates that you have to do. Okay, so any questions? I think I may have gone a little fast in the proof part. I also don't know if I'm missing the online. Okay. Right, so if you still are not sort of convinced by the proof, I would encourage you to just go through the proof. Like everything is written here. You can just go and verify step by step, and if something is not clear, you can maybe ask me tomorrow.
So can I bunch of it as also be a part of somewhere hard?
You can estimate that R, right? So is it let's say you go over all pairs of positive and negative points, right? And find the closest positive negative point pair. So then R is likely to be, oh, you said R. R is the length of the largest vector. Sorry. I got confused with base. So R is simply this. So I guess you're talking about W star. And I was answering about W star. Yeah. So for W star, you just maybe, find the closest pair of positive negative points and take half their distance. Right. So then one over that is roughly going to be the value of that length of W star. I mean, it won't be exactly that, but it will be proportional to that.
So then, so we give a bunch of data, and let's say we don't know whether it is really separated. Whether there is a weakness. What you are saying is that it's in certain bound part that not abuse are which you can compute. Yeah, you should be linearly separable. There is some bound that you are able to compute it. Yes. And now we will just take this to run the perceptron for those many iterations. And if it hasn't formed a separator at that stage, would you be able to prove that the original data was not linearly safe?
Yes. Although what I said about the estimating the value of a star, that's not completely accurate. So there are more accurate ways to estimate that value. You use that value that will tell you that the data is not linearly separated. So here there is another factor that your data in the real world, it's not always like the data actually is linearly separable, but there is some noise in the data. And so that noise affects various things. So then your algorithm has to be somewhat more robust to handle the noise. Like if the noise is very small, then this point is shifted here or there a little bit. So then that does not affect linear separability. But if there are some points with a lot of noise, so that if this guy goes over there, then those things become challenging. And then there are other more complicated ways to handle those things. Like you have to label something as outliers and blah, blah, blah. Like there are other things that keep it. But the very basic thing is essentially linear. Okay, so let me also say one more thing here, which is that, so if you go back to this situation, right, which is just more representative of the real world, right? So if you have some data like this, right, you cannot, naturally there is no linear separator. Right? Let me actually give you a more better example. So let's say you have some negative data points in 2 dimensions, right? And then you have some positive data points. So there is no way that this is linearly separable, right? You can never find a line which has the negative points on one side and positive points on one other side. So what do?
Subject transformation.
Correct. So from this example would be basically, right? So here your data points are in the form X. Like these are some X, I, Y. I should go prefix that one. So the data is in the form of x1, x2, right? Like 2 coordinates in this. So if I have to convert this data into 3D, where it will become x1, x2, and the length of this x1, x2. So square root of non x for square root. x1 square plus x2 square. Once I do this, the picture will sort of look like this. So I'm basically projecting these points in 3 dimensions. So these green points, they will become a circle over here, and the red points will become another circle over here. And in this 3D space, you can find a 2D plane separating the green from the red. So there are ways to deal with non-linearity in the data. Essentially, we're projecting them into higher dimensional spaces or things like that. So we'll go into those things later. But most of the machine learning algorithms, the way they work is that they take the data point which is in some space. I mean, you tried your best to come up with a good representation for the data. Right? Unfortunately, that representation still does not make positive or negative, whatever you want to do, like as linearly separable. So then you have some other machine learning model, some neural network or some support vector machine or something. So the first part of that, what it is going to do is that it is going to basically keep projecting the data into more and more different spaces, and eventually it will project it into some space where positive and negative samples are linearly separate, and then it finds a linear separator between. So this linear separator thing is essentially at it's the starting point of all these algorithms. And so that's the last thing that you do essentially. But anyway, so that circle thing is a good example to keep in mind. Okay, so let us stop here.